This is Timothy Chu. I'm a second year PhD student of Professor Gary Miller over here. And today I'm going to be presenting on two metrics which we think are principal metrics to use in clustering, which is a problem in machine learning. They're called the edge squared metric and the nearest neighbor metric. If you haven't heard of these before, don't worry. We will be defining them through the course of our talk. So before I get into the sort of like nuts and bolts and proofs of our talk, I sort of want to give like a high level overview. If you take away nothing else from this talk, what are we really trying to do here? So the problem that Gary and I think Professor Donald Sheehy from the University of Connecticut were exploring was, in many machine learning problems, from clustering to manifold learning, there is use of a metric under the hood. So for those of you who are familiar with clustering, or k-means, there's the Euclidean metric. And we would like to explore metrics that are principled. We'd like to explore the sort of theoretical foundation for what makes a metric good or bad for certain machine learning problems. Keep in mind we are doing this all from a theoretical point of view, because we are theoreticians. And of course, because we're theoreticians, we'd like to be able to prove some results about the metrics that we're looking at. We're not, we do have a few experiments that we ran, but we're not like just running 1,000 experiments and saying, hey, this is great. So there are two candidate metrics that will have suitable properties. And what a suitable property is, we'll define soon. These candidate metrics are the edge squared metric, which was defined by Vincent and Bengio, 2003. And the nearest neighbor metric, which was sort of defined by, I believe, Professor Miller and a few other people. They look very different on the surface, so the result of this talk, the main result, is showing that these two are equal. Of course, we'll show why we care, and we'll show how we do it. So just to recap at the high level, we're basically trying to explore metrics usable in machine learning and the properties that we'd like them to have. We explore two candidate metrics, the edge squared metric and the nearest neighbor metric. On the surface, they look very different, and they were proposed by different people. We will in fact show they are the same, and thus provide a theoretical guarantee that you can actually reason about metrics like these. Sound good? And if you remember nothing else from this presentation, remembering the high-level overview of this slide will actually suffice.
Could I ask a general question? Metric over what objects?
Oh, yeah.
Objects are you commuting the distance of?
Yes. So these are points in Euclidean space, in high-dimensional.
Sets of points, or
just points within a set of points. So normally, you'll have a set of points, and you might want to find the distance between two of them.
okay.
Does that answer your question?
Yeah.
Oh, sorry. Great. So the rough roadmap for how this talk will look is we'll just explore metrics for clustering. We'll try to lay down a few properties and get our hands messy with what properties we'd like. Then we'd like to formally define the two metrics of our study. And then we're going to ask what we can prove about them. And we're actually going to provide some details of our proof. So first, let's ask, what is clustering? Because I know this is sort of a theoretical computer science crowd. From a scale of I have no idea what clustering is, to yes, this is old and I know what this is, where are people at?
It should be a circle.
Okay, so...
I'm answering your question.
Yeah? Oh, you're answering a question. You know what it is.
I don't know what you...
Oh, sorry, there's like a sliding
We're
scale.
supposed to put our hand at a different altitude?
Yeah, your hand is a different altitude. Okay, I guess it didn't actually work that well. But some people know what clustering is and other people don't like to answer questions. So basically the question is, how do you partition data points, usually which come from a probability distribution in clusters? So here I presented, two examples of points you might want to cluster. This first example, we have a bunch of points. Probably you want to cluster them with the colors you show. Second example, you have a different set of data points. Probably you want to cluster them with these two data points. So there are popular methods like k-means, k-medians, for those of you who have heard of those, that sort of use a metric under the hood. And the metric sort of weights how close the 2 points are. Normally practitioners use the Euclidean metric. And we will be going through a quick exploration for when that Euclidean metric seems to break down. So actually, intuition suggests that when 2 points are in the same cluster, we actually want their distance to be considered close, even if their Euclidean distance is far. So I guess one audience question I'd like to ask is, why would this be the case? Why would you actually want 2 points in the same cluster to be close if their Euclidean distance is far? Can you come up with examples for which this is the right thing to be doing? This is sort of like a silent audience question, so just take 30 seconds or so to think about it for just a bit. Just think about it for just a bit, for 10 more seconds, and we'll get to our talk's answer.
Another deep learning one?
Kind of. Kind of. I will not be going down that hole today. So actually, I'm actually just going to cut to the next slide for the right example. So if you look at this point set in this corner, you see the points labels A, B, and C. Their Euclidean distance is roughly the same. But if you were looking at an actual point, you'd probably say that A and B were more similar than B is, or A and C. That would probably be your guess based on looking at this. And another example is within management learning. These 2 points and these 2 points are the same distance apart. But standard machine learning intuition tells you that these 2 points are probably closer together than these 2 points. Other examples include if you wanted to cluster this set, which is sort of a ring and a circle inside, sort of the target sign. You probably actually want this point and this point to be considered close together because they're sort of connected by a bunch of data points. So they're probably similar things in the intermediate space. Whereas you probably want something between the rings to be considered far apart. There'll be a few more examples, such as the half moon. And you might ask, what are these colors? Why is this colored red and blue, and why is this colored gray and yellow? It turns out that standard machine learning techniques, such as k-means clustering, will cluster it into the red set and the blue set, and into the yellow set and the gray set. It's probably not what you want. Probably you want to color this in one cluster and then bring in another color, and also this half moon in one color and this half moon in the other color. You probably want them to be part of 2 separate clusters. So we'll be exploring metrics, or we'll be laying down 2 metrics, which will actually give us a desired property, such that it clusters the other property. Now we're going to talk about what metrics actually have these properties. The property that 2 points are considered close together if they're in the same cluster, even if their Euclidean distance is far. The first thing we'll talk about is the edge squared metric. So I've laid down a very formal definition here in LaTeX. I'll give people just a few minutes to read over this. Just because I know, LaTeX formulas can be a little bit, takes a little bit of time to decipher. And people read this text, is like the backlight goes up.
Yeah, I think it's okay.
Okay.
You could turn off some of the.
I'll try to turn off
Make it a bit easier to see. That way maybe.
Yeah, these are the ones you want to turn off,
Yeah.
the ceiling lights. Yeah, I can
Does
see
that work? People like being in the dark? Cool, so this is, a very formal definition. Is there sort of like a human English understandable, what am I actually trying to do here? What are people actually trying to do here? Yeah.
The shortest path, using the edge, the square of the distance between each pair of points along the path.
Yep, it's just the shortest path problem, where the distances between each point are considered the Euclidean distance squared. We'll claim, this is of course highly dependent on what point sets you have, so the distance between 2 points depends on the configuration of the other points. And what property do we want this metric to have again? And does this metric have our desired property?
So K is not fixed, so K could be, the number of points could be, is not fixed, it could be anything?
So in this definition, the number of points can be anything, yes. But usually you deal with a fixed point set. So you first lay down your point set and then you define your distance. But there's no restriction on how many points you can have. Does that answer your question? Yeah, so what properties do we want this metric to have again? Anyone from the audience?
2 points should be close even if their Euclidean distance is far.
Yep, 2 points in the same cluster should be close. There's a bunch of points in between them, even if their Euclidean distance is far. Does this have the property we want? Can anyone give a brief explanation? It's okay if you're wrong, better wrong than vague. Yeah. Oh, well, we'll let someone else in the audience think for a little bit.
It should be perfect because if the distance between the points is small, the square distance is even smaller.
Yep.
And if the distance is large, the square is become very large.
Yep, absolutely. So if the distance between 2 points is small, then the square distance is even smaller, and if it's large, then the square distance is even larger. So if you imagine you have your points, if you have 2 points here and here, and there are no data points in between them, the distance will be this gigantic thing squared. But if you lay down a ton of Euclidean, a ton of points in between them, you're suddenly adding the square to the small distances, which will become much smaller than if you didn't have those points in between. Seem good? Cool. So this is one example of a metric. This was first proposed by, I think, Vincent and Joshua Bengio in 2003 in the context of semi-supervised learning. And it's nice because, you know, it uses some very common technology, right? Like shortest paths and graphs. Very common, very famous tool.
Is there a good reason for squaring it rather than cubing it?
No.
Okay.
It turns out that the proofs we will show will actually be harder with cubing it, but there's no like great reason for squaring it, not cubing. Yeah. So this was actually tested in practice by a few engineers from Google and the Toyota Institute of Technology, where I think Howard and Blum have now left to. It turned out to do pretty well in a number of practical data sets. Although we don't actually know how much of that is them cooking the books and how much of that is like it actually does well. So take this with a grain of salt. So now we're going to move on to the second definition, the nearest neighbor metric. And again, in this talk, there are only really two definitions to keep a handle on. The n-squared and the nearest neighbor metric. Once you have those, we're actually pretty good. So the nearest neighbor metric will be defined in this terrible way. But it will be actually pretty nice, I think, under the hood. We're first going to define the length of a path winding through Euclidean space. So this path, unlike the shortest path of graphs, does not need to be a graph path. It can just be any path through space. So here's this big, ugly integral that defines the length of a path. So again, I'll give people a minute or two to digest what this definition is. And this definition, again, is one of our core definitions. If you know this and you know the n-squared, you've probably taken like 50% of our talk already. I might have
Gamma
had,
is a path, right?
sorry?
Gamma
Oh yes,
is
gamma
path.
here is a path, that is correct.
And what minimize the gamma?
Yes, in the end we want to minimize it. So we haven't defined the metric yet. We first want to lay down how we define path lengths. So this is a big, ugly calculus formula. But what is it really saying? It's really trying to address the problem of given 2 points in space. How we can find the minimum distance, or how we can find the length of the path between these. So here any path can be unrestricted. It can do whatever you want. It can even cross itself. Oh, can people see this? Maybe not.
Well, we need to get a better marker for one thing.
Yeah. I see Gary. That's right. Of course, this doesn't work super well, but so what this is really saying is given 2 data points, pretend there are a whole bunch of points laying out in space. We want to find the length of any path going through them. This is sort of a general definition. Normally, what you do is you just integrate over the curve. But here, what you do instead, there's a slight modification, where the length of each infinitesimal piece is weighted by how close it is to the nearest neighbor in your point set. So this is a definition that depends on your initial set of points. Remember our paradigm is that we have a bunch of points that we observed. And for any point along this path, the amount that you sort of, the amount that you sort of charge it, the amount that it costs to go there, is proportional to the nearest neighbor distance to the nearest point in the set. Does that make sense to people? We're just trying to find the length of the path, freely walking through space, based on our initial data points. And from this, we will define the nearest neighbor. So this is the first part of our definition of the nearest neighbor. Are we good on that so far? Cool. So I'll give a quick exercise to see, get our hands dirty into this metric, because this is one of the core definitions, which is that, let's say you had.
Could you explain that second term? Is that gamma prime or just?
Yeah, this is gamma prime. This is just the length of a Euclidean infinitesimal.
That's the speed term.
Yeah, it's sort of like.
That's how fast you're traversing the curve.
Yeah. So in normal path integrals, you wouldn't have this first term at all. It would just be 1. And the length of a path would just be the integral of this derivative.
The velocity, the speed with which you traverse the term. As you're going along, how fast are you going?
You're integrating the speed, which is essentially distance. Then it's just the distance. The length, then it's just the length of it. If you didn't have the nnx,
Yeah,
then this would be just the length, the Euclidean length of that curve.
that is correct. Yes.
Okay.
So
It's
that's sort of what
adjusting the
this-
Euclidean length by the nearest neighbor function.
Yep. So basically, we're tweaking what you normally charge this path, but on any little infinitesimal you walk on, you're saying it's weighted by the nearest neighbor distance, which means it's shorter if you go close to a point, and it's farther if you're far away from the point. So This point is weighted by a lot. This point is weighted by a little. So just to get our hands a little, oh, I should actually jump to the punchline here real quick, which is the definition of the nearest neighbor metric, which is just the infimum of our previous definition over all possible paths times 4. Don't worry about this one, it's just a normalized. But we basically want to take the shortest path from these 2 points, where we define the length of the path in this sort of kind of offbeat and unusual way. Now, here, before I continue, I actually want to ask just a few basic questions, which is, again, what property did we want this metric to have? You know by now. And does this metric have that property? Oh, I'm so sorry.
Oh, that's good that knows the answer.
Vote a friend, yeah.
I'm so sorry. So maybe I'll do 1 or 2 examples just so we get a little familiar with this definition. Again, this is one of our core definitions, so it's actually worth it to spend this time understanding what we're doing here. Which is that, let's say you had all your points sort of on the ring of a semicircle. Okay? You have a bunch of data points that look like this. Now, our previous definition, which I'll put on the board, the path length, you can take the path that sort of wanders near these points up top, but has a longer Euclidean length. Or you could take just this path that cuts across the center. Okay? Based on our definition here, which path do you think is shorter?
Top one.
The top one. Why is that?
Not being charged.
Right, you're not being charged much. For each of these points, it only costs this tiny nearest neighbor distance. Whereas if you take a corresponding point here, you're getting charged by this ridiculously large distance. Right? When I say charge, I mean that's sort of the scalar multiple of the Euclidean distance. So this again has a property that if we didn't have these data points in between, the shortest path would be pretty cool. But if we did have these data points in between, suddenly we have the opportunity to sort of ride this highway on top. And in fact show that these 2 points are closer together. So this is a little brief explanation for why this metric has the property we want. Basically, when you have more data points, you can sort of take a path that goes close to them, and that path will be cheap, which makes this infimum cheaper.
So that NN is not squared.
No, it's not squared. That nearest neighbor is not in fact squared.
So just to make sure there's some sufficiently large amount you could push these points up where now it would be shorter.
Oh, absolutely.
Yeah.
Right? If you had a point like this, and you just take this tower all the way up, right? It's probably cheaper to walk this way than it is to walk on top, yeah? So yes, that is in fact a great observation. Cool, so the quick recap of what we've done so far is we define the edge squared metric. Again, edge squared metric is you just have a bunch of points. Distance between 2 points is the shortest distance on the complete graph where the edge lengths are equal to the edge distance squared. And we've defined the nearest neighbor metric. So this will sound really banal to those of you who are following, or to those of you who are still struggling a little bit. Just recap to yourself a short way to summarize these 2 metrics in your head. And the reason I'm doing this, and I'm going so slow, is because the rest of the talk will be way, way easier if you have a solid grasp of what these 2 metrics are really trying to say. We'll try and play around with a few examples. Maybe even go back to the clustering pictures we had before, 2 half moons. And maybe a long sandwich of points. And even points that look like this. I'm trying to play around with these examples and nearest neighbor distances between points within these. So I'm just going to give the audience 20 seconds or so to do this in their head real quick.
Sorry, assuming the underlying point set lies in Euclidean space, is that important for this kind of thing? Or can it be any kind of metric space for you?
For our proofs, it's important they're in Euclidean space.
Okay.
That's actually a common assumption that I believe machine learners make.
Yeah, which is fine.
I don't actually know what happens if we use more general metrics. Yeah, that is certainly a good question. We haven't explored that before.
We're in 2 dimensions.
Sorry?
Are we in 2 dimensions?
We are not necessarily in 2 dimensions. We are in fact in arbitrary dimensions. I can only draw on a 2-dimensional board, unfortunately. Cool, so now we went through, the properties we want metrics to have, and definitions of metrics that satisfy such properties, 2 example metrics that have been proposed. And now we sort of want to get to the proofs. So before I get to the proofs, again, I'm just going to be slow and like walk at a snail's pace. Do we have any questions so far about the definition of these metrics, besides the ones already asked? Yes?
How easy is it to compute the full metric, like given the point set in Euclidean space?
Mm-hmm. Yep, so the question is, given a point set, how easy it is to compute these metrics? Our short answer is, unfortunately, we don't have a great algorithm to do so. So right now, our fastest algorithm is just straight up Dijkstra. We believe there are faster algorithms, and that's sort of our future work. We have reason to believe this. But for now, we basically are just running Dijkstra's algorithm.
The edge squared does have a polynomial time.
Where you assume d is dimension is constant.
The edge squared metric is polynomial time, right?
Oh, it is? Oh.
Because you just make the quadratic graph and then you just.
Oh, yes, but that's Dijkstra, or that's Flood-Warshall or whatever.
Yeah, but the nearest neighbor, it's not clear so far, right?
Yep, that's correct. So I think what Professor Miller is saying is for the edge squared, you can just run a Dijkstra, because it's short path. For the nearest neighbor, who knows, right? You have infinitely many paths through space that you could want to. So yeah, any other questions? Yes?
Maybe I'm jumping in the gun here. What exactly is the sense in which they're equivalent?
But for any 2 points in the data set, the nearest neighbor metric distance is exactly the same as the edge squared distance.
That's why the 4 is there.
That's where the 4 is there, yeah.
But you have exact equality up to a scalar factor. Yes?
To follow up on Kyle's question, in the nearest neighbor metric, is there a good reason to take that distance to like linearly instead of super or sublinearly?
Yes, that is a good question. No, there isn't.
Okay.
You could in fact take like nearest neighbor to the power of like 10. You could in fact take like second nearest neighbor or a variety of other functions that have the same properties as well. There are a number of metrics that have our desired clustering property. It's just these are 2 metrics that we have to do. But that is the subject of future work. And we'll come up with those. Great. I think I'll be moving on for now. So, sorry, any last burning questions that people think are super important or even super trivial? Super trivial questions are also great. Okay, everybody understands everything completely? This happens at every theory talk, right? Everybody always understands everything that's said. Sorry, I'm just... So great, we'll just move on to the proofs now, which is what we can prove about the edge squared metric. Previous work showed that the nearest neighbor was a 3 approximation of the edge squared metric. We already said what we're going to talk, but I'm going to give a quick roadmap of what we're going to do from this point onwards. We're going to show why do we care about this result. It's kind of cute, but like really who cares? We're going to go into a little more detail in previous work. We're going to sketch the outline of how we prove it. And basically after we prove it, we're going to have a few open questions and straight ends, but the talk will end there. So really we have 3 parts. Why do we care, previous work, and how do we prove our results? So why do we care? Well, this is kind of the first proof that we know of, where we take, a graph metric, like a graph geodesic metric, equate it to this very continuous metric, where you can take an arbitrary number of paths between any 2 points. Of course, this speeds up the computation of the nearest neighbor metric, because now you can compute it exactly as it is approximately. Also, we like theoretical proofs, and this is a theoretical proof on 2 metrics in this space that we're exploring. Of course, we hope that this opens a new line of work and inquiry with our methods, but who knows? We can really say on that. So previous work, this is Cohen, the same Cohen who was actually mentioned at the beginning of this talk. Fassi, Miller, Neri, and Sheehy, and I'm missing a guy, Amaya Vellinger. 2015 obtained a 3 approximation. A bunch of smart people worked on the equality case, but they could not even do it for 4 points in 2 dimensions for quite some time. So in this talk, we actually knock off all dimensions and all number of points, which is slightly remarkable. And now we're going to go to how we prove it. So this is the last portion of the talk. We're going to sketch the outline of how we prove these 2 metrics are equal. And we're also going to hopefully give you a reason why you should care about these methods. We think this is actually kind of an interesting proof. So first, there are going to be 2 steps. We want to show the nearest neighbor distance is less than the edge squared distance. And we want to show that the nearest neighbor distance is greater than the edge squared distance, well, greater than or equal to. And of course, combined, this gives us that they're equal. Now my question is, I claim that this side is easy. In fact, it's not hard to show that the edge squared metric is greater than or equal to the nearest neighbor metric. My question for all of you is, why might this be? You can take wild stabs at it, But why might this be easy? And if you understand this part, you'll sort of understand why we even suspect it. Yes?
I mean, couldn't you just take gamma to be the one that like goes from like the start to the first point on the shortest edge square path and the next one?
Yep, that's great. I probably should have had more time for people to think about it, because that was a fairly quick answer. But if you haven't thought about it for that much, take just a little bit longer to think about it. That is the correct answer, and I'll be sketching that in just a bit. So try and think to yourself why the edge squared distance is always greater than the nearest neighbor distance, greater than or equal to. Cool. So I believe, as Nick mentioned, one path that you could possibly take if you wanted to travel between these 2 points is the path that, exactly follows the line segments between 2 points. We won't show it now here, but it's actually not too hard to prove that this distance will be the edge squared distance if you restrict yourself to straight line segments between data points. The reason this is you do a computation on 2 points, you draw the ordinary cells in. Don't worry about it too much. But one way you can treat the nearest neighbor being less than the edge squared is saying the edge squared is in fact a discrete approximation of the nearest neighbor distance. It's when you hard restrict yourself to paths that are polygonal along your data points. So why would the nearest neighbor then be greater than the edge squared distance? Well, that's the hard part of the proof, and that's the part we'll show. That's what we're going to outline for the rest of the talk. So the nice thing about this is when you look at the nearest neighbor metric, it's a big calculus definition, right? Maybe you have to use calculus of variations, this kind of stuff in physics. Actually, our proof is entirely discrete. We never use a single integral in our proof. Our tools that we are going to use include L1 embedding, projections, the Kirszbraun theorem, which is sort of a contraction theorem in computational geometry, very cool, and basic Dijkstra's algorithm. So it's actually extremely low technology with the exception of this rather remarkable theorem proved by Kirszbraun in 1934. We'll be going over what that is later in the talk. And the outline for the rest of the talk, the outline for how we're going to prove it, is we're going to say, fix a point S and T. So fix your starting point. We only want to show that for these 2 points, the edge squared distance is the same as the nearest neighbor distance. Because, you picked S and T arbitrarily. To do that, we're going to find an embedding. So we're going to take this point set, embed it into some other point set, such that two properties actually. The edge squared distance does not change. So we're going to maybe embed this into some other crazy point set. Maybe it's in multiple dimensions, where they're the same number of points, and I need the same number of points. The edge squared distance doesn't change, but the nearest neighbor metric only shrinks. So the name of the game is we're trying to shrink the nearest neighbor metric while keeping the edge squared metric the same. Right? It's sort of pushing the boundaries of this inequality. And on this restricted point set, on this embedding, we're going to try to show that the nearest neighbor is in fact equal to the edge squared distance. So again, the basic name of the game is given our initial arbitrary point set, we're going to find an embedding into a structured point set. In fact, this point set will have very nice structure, which we'll talk about later. Once we have this embedding on the structured point set, it becomes easy to prove that the nearest neighbor is equal to the edge squared. Because you only shrunk the nearest neighbor, but you did not change the edge squared distance, you will in fact get this inequality if you show that they're equal in the embedding. Is that clear to people so far? People have questions about this outline? And this outline is sort of the majority of the proof sketch, so this is sort of where the battle is won. Questions, comments, holes in the argument?
So I have a question. I'm
Yes.
not clear about the significance of using edge square distance. Why not edge distance? Where are you using the square?
Great. So what happens if we use edge distance between these 2 points? Well, distance is always just going to be Euclidean distance, right? Like if I just use edge distance between 2 points to find their distance, the shortest path on my graph is always just going to be a straight line distance. So edge squared has a property that we might take like this path up top rather than this path at the bottom. Why did we use edge squared? Sorry, did that answer your question? Or there, maybe like, are you asking why did we use edge cubed or some other crazy definition? Or where in the proof are we using edge
beginning
squared?
of the talk that squaring shrinks small things and expands big things.
But are you also asking where in the proof are we using the fact that it's edge squared?
Yeah.
So the part of the proof we're using edge squared is when we're going to find this embedding, and this embedding is highly dependent on the edge squared metric. right? So the embedding that we actually create, which I conveniently haven't said, but spoiler, we just embed these points into the corners of a box, like a rectangular prism, which is very nice. Only works because we have the x squared measure. So that's sort of the, does that sort of answer give you a little hint as to why x squared is important?
Okay. Yeah.
Very critical for this embedding. And nearest neighbor, not nearest neighbor to the power of k, or not any other function, was important, because within this embedding you can prove this property, x squared equals nearest neighbor, very nicely. So again, high level overview, embedding preserves x squared, shrinks nearest neighbor, super nice set of points where you can prove nice things on it. You get this one
From S to T, right?
Yeah, only from S to T.
But other vertices can get closer?
Yeah, other vertices can get closer. So you might actually collapse two vertices to be the same thing. Doesn't matter, because you're only considering S to T distances.
And this may be a higher dimensional space then.
Yep, you may embed into a higher dimensional space. So it turns out that these points will embed to the corner of an n-dimensional box, which is much higher than the 2 dimensions of these points at all. Cool, are we good with this outline? Oh, yes.
Sorry, is the n of n dimensional the number of points along the path?
Ah, yes,
Square
yes.
distance?
It's a number of points on this that we laid out. Cool, are we good with this outline so far? Again, just very basic, there's an embedding, there's some cool technology under the hood. Our core work, of course, is just showing what this embedding is and why it works, yes?
Why n and not log n dimensional?
So you could probably do log n dimensional, because of, Johnson-Lindenstrauss or something, is that right?
Yeah. Sure, but I guess it's out of the.
Yeah, so I haven't thought about that too closely, but Johnson-Lindenstrauss doesn't give you exact things, it gives you like an approximation term. Maybe you could do log n dimensional, I'm not exactly sure. But since we're only trying to prove these are equal and not deal with runtime guarantees yet, it suffices to use n dimensions. So basically that's a great question. I can't tell you off the top of my head. Oops. Cool. So tools in our work include the Kirszbraun theorem, a whole bunch of stuff. I'm actually going to quickly show you what the Kirszbraun theorem is. This is in fact the core piece of technology that will make our proof work. I actually claim that once you know what the Kirszbraun theorem is, it doesn't actually take too much work to piece together our proof from there. So I will be going over what the Kirszbraun theorem is. The reason I'm doing that is once you have that, and once you have our outline, the rest of our proof actually follows pretty nice. So the Kirszbraun theorem is actually this magical theorem in Hilbert space, but it also works in real spaces, or Euclidean space as well, which basically says, there's a big formal definition here. What it basically says is, let's say you have a function from a point set to another point set. This function just happens to contract all your Euclidean distances. Okay? So you have some let's say you have a point set, you have another point set, such that all your pairwise Euclidean distances shrink. So maybe this point maps to this one, this point maps to this one, this point maps to this one. These are two separate worlds. The claim of the Kirszbraun theorem is that not only do your pairwise distances shrink here, but you can find an extension to the entire space, such that all pairwise Euclidean distances shrink. So basically what you're saying is, given a function that has a nice property, you can extend it to the entirety of the Euclidean space. This is not a trivial theorem. It's in fact a very fun exercise to try and prove this theorem on 3 points. I do have a lot of time left for this talk, right?
Yeah, 10, 15 minutes.
Great. So my question for you is going to then be, can you try and come up with a construction for 3 points? Just to get your hands a little dirty into what this theorem says. Again, if you followed none of the rest of the talk, if you just got lost at square one, this is a very self-contained theorem right here, so you can suddenly jump back on the train.
Excuse me? Okay, you have f small as a function from set of points, and then big F is function from all the space, right?
Yes.
But if you just take 2 points,
Yep.
you can always project them so they're closer to each other. Does it mean that there is big F for each S and T?
Sorry.
I think you forgot to write that capital F.
Oh, capital F, sorry, capital F, yes. Capital F matches little f on the point set.
Yeah.
Yes, I forgot. Otherwise you can contract it.
Extend it.
Yes, a great point.
All points.
There. Cool, so can we think about ways we might prove it for 3 points in 2 dimensions?
What about just saying having a matrix, a linear transformation?
Yes, you might think a linear transform would work. That does not work. Here's why it doesn't work. Let's say you took, take this point here, right? The distance from here to this line is pretty far. If it was a linear transform, it would map this line to this line. Sorry, give me a moment. Right, sorry, if it was a linear transform, it would map this midpoint here to this midpoint here, right? Any linear transform must map midpoints to midpoints. But this distance is longer than this distance.
Even though the corners are closer.
Right. You can imagine a very pathological case where you have these 3 points. Your midpoint is here, and let's say the image of this triangle that you want to map to is this. This midpoint starts out extremely close to this point, but when you try a linear transform, it gets very far away. Does that kind of make sense?
Yeah, my idea is no good.
Yeah, so this is why it's so hard. Right, this is why it took, this guy, this Polish guy, a gigantic thesis to figure this out. So actually,
How do you do it then?
great. So for 3 dimensions, one thing you can try to do, 3 points, is you can imagine, let's say that these 2 lengths, pretend that, these 2 lengths were equal, these 2 lengths were equal. So let's pretend these lengths were equal, these lengths were equal, and the last distance is contracted. This is a very special case of our 3-point example. What you can imagine doing is folding this point over a crease until it matches to this point. Right, so pretend you're a piece of paper. Fold this point over until you get this point. Because folding preserves these 2 distances, you can always do this, as long as these distances are the same. And once you have a folded piece of paper, your distances must contract. Because your distances along the folded piece of paper must be longer than your distances in the space. Yes, question?
Do you have any additional assumption on any property for the capital function f? Is it usually not continuous or anything like that, or can it be
Is it always
well behaved in some sense, or could it just be completely weird, mapping things all over the place?
Yeah, so what properties does capital F have? A, is it continuous? Do you assume it's continuous? Is it always this folding sample? Both are great questions. My claim is it has to be continuous. Can anyone see why?
Oh, it's Lipschitz.
Yeah, it has to be Lipschitz, right? It has to be
Right,
one
never
Lipschitz.
mind.
So it has to be continuous. That's a great question.
Yeah.
The second question is it always, can you always do it with folding, maybe in higher dimensions? Our answer is maybe. The reason we say that is there was a recent paper about this where I believe they only do kind of folding-like operations. They do a little bit of cutting and pasting it back together in the end. But unfortunately, I haven't gotten sufficiently far in that proof to say for sure. But right now, Professor Miller and I believe that for all practical purposes, it's most things roughly look like folding a piece of paper.
I'm pretty sure there's some finite sequence of operations that you do that are sort of geometric.
Yep, there's a finite sequence of geometric operations. I believe you do cutting and folding and repasting. But in fact, the intuition from a paper is not embedded. And in fact, this is compute. You can actually compute what this embedding is. It's one of those theorems in computational geometry. Cool. So does everyone sort of get the purpose of does everyone get what this problem is saying? And why it might be true for just 3 points, but how it's also not entirely obvious that it's true? Cool. So again, if you understood none of the rest of the talk, this is a very self-contained bit. Now we'll go back to our proof skeleton, and I'm only going to try and outline why this is important in our proof. I guess I still have time, so I can try to go through the full proof. But the basic outline is, the name of the game is we want an embedding that preserves edge squared distances while shrinking nearest neighbor distances. Turns out if you shrink all your Euclidean distances, you shrink your nearest neighbor distances for free. Why is that? Well, because the nearest neighbor distance is the integral of, a product of the nearest neighbor times your, Euclidean infinitesimal. If your Euclidean distances shrink, both parts of your product shrink, yeah? So, this path length shrinks and the charge shrinks. So if in fact you have an embedding that shrinks Euclidean distance, you have an embedding that shrinks nearest neighbor distance for free. Right? So now we're saying, we're trying to find a contracted map on our entire space that shrinks Euclidean distance. That sort of reminds us of what the Kirszbraun theorem says. And the way we construct this embedding is we sort of want to maximally contract all the other points, the discrete pairwise points, their Euclidean distance, while keeping ST distance the same. How can we do that? Again, to reiterate the question, we want to shrink all these other pairwise distances, this time for points in our data set, while preserving ST metric. What's the best way that we can do that? How much can we shrink each distance by? what's one possible way you can shrink a whole bunch of other distances while preserving?
Sorry. So you like define the function on like S and T, and then so you define like some function mapping S and T to two things like a little f, and then you extend it.
Yep, absolutely. And how do you find the little f though? That's the question. How do you actually find the little f that contracts for Euclidean distances? And what are some possible ways? You've seen this in like graph algorithms classes. Okay, maybe I'm underspecifying the problem a bit, but I'll just give the answer here and we can see why it answers the question. What you'll do is you'll start running a single source Dijkstra from S, right? So maybe you'll have, if you have these points, let's say this is P1, P2, all the way to like Pn or something. What you'll do is, if you just had a graph, you could in fact make each edge distance, so you can define d of Pi, Pj, to equal the distance from your source to Pi minus your distance from your source to Pj. Of course, you have to put an absolute value here because all distances are positive.
This is an edge squared metric, or
This is in any metric. But yes, this is a, sorry. Give me a moment to clarify what I'm trying to do here. Sorry, just give me one moment. Sorry, let me actually back up for a little bit and try to just go through the high-level overview again. We want a metric embedding from S that preserves S to T edge squared distance. What we can do is we can start from S, run a Dijkstra's on the edge squared distance. Then we can, create new distances so that we create new, this is the edge squared distance. Yeah. Trevor, run a Dijkstra's on this point. We, on the edge squared distances from this point. You embed that into a line, right? This is a line embedding. So you just lay down your distances in the edge squared metric, subsequently on a line. Then you take the square root of all distances in the line. And I claim that that result will actually give you a set of points such that the edge squared distance is the same, but all your Euclidean distances contrast. So again, the procedure is take your edge squared graph, run a Dijkstra's, lay down your points on a line where the point, the coordinate of your line is equal to the distance from a single source. Square root of those distances, and in fact, you will find that you get a nice Euclidean box in the end. Turns out that you can extend that map to your entire space. So all you have to do is prove that the nearest neighbor is equal to the edge squared of the box. That actually turns out to not be so hard. I will admit the proof here, but that's a rough skeleton of what we're trying to do. Yes, question?
Yeah, I'm not sure understood the jump between laying down points in the line and then square rooting the distances.
Ah, great. So when I lay down the points in the line, I've now created a graph such that the distance from S on that graph is preserved, right? But that's the edge squared distance. So if I want an initial set of points such that the edge squared distance is preserved, sorry, let me actually just write this out formally. I apologize for this because I didn't think I had time to go through the proof. So I'll try to lay down a few words for this.
How about just do an example of 3 or 4 points?
Great, I'll do an example with 3 points. That's a great idea.
But aren't you going to go to higher dimension?
Oh, yes.
So far you haven't said.
Yeah, do 4 points for them then.
Fine, I'll do 4 points. I'll do 4 points for you. So let's say you have 4 points, okay? I'm just going to lay down a few distances. This is 1, this is 1, this is 1, this is, I don't know, 1.9.
These are edge squared distances, or
yeah, these are edge squared distances. Okay. This is edge squared. Oh, sorry. Actually, the property.
like squared Euclidean distance, what would that be?
Let's say this is our edge distances. So we have 4 points, and I've specified the edge distances between them. Just pretend the distance between these two is long enough not to matter for now. But I can lay down something there too. So these are your 4 points. We're first going to find the edge squared graph. The edge squared graph is going to look something like this. 1 squared, 1 squared, 1 squared, 4, 1.9 squared. This other distance is too long to matter, let's say. Okay. So it turns out the shortest path here, well, the shortest path from this point to this point, the edge squared graph is 2. Right, so if this is S, T, S, this is T. What we're going to do is this distance is now 2, called P1 and P2. So we're going to find another embedding to So the line, S. In fact, all these distances are going to be 1, right? Because the shortest path from here to here is going this way and going this way. So in fact, this is a graph such that the shortest path from S is the same as the shortest path from S here. What we're going to do now is we're going to take the square root of these distances, y, we're going to see in just a bit. But when we take the square root of these distances, this distance is 2, the square root of that is square root 2. So it turns out that
You're taking the square root of 1 squared or 1?
O of 1. For any 2 points, we're going to take the distance between them and square root.
Oh, right, okay, yeah, that makes sense. No, I'm serious.
So it turns out that this is going to end up mapping onto the corners of a box.
Yeah.
We're taking the square root of all distances, not just adjacent distances. Check for yourself that this box satisfies the property. So by box, I mean like a rectangular prism. This is going to be S, this is going to be P1, this is going to be P2, and this is going to be T. What's the distance between S and P2? Square root 2. What's the distance between S and T? What's the distance between P1 and T? Square root 2. And in fact, those are the square root of these distances. Now, what did we do with this chain of reasoning? Well, try to compute squared distance, edge squared distances on this box. What's the edge squared distance from S to P2? It's 2, right? Same as in here. What's the edge squared distance from P1 to T? Also 2. Same as in here. Distance from S to T is 3, edge squared distance, is the same as it is in the initial picture. And so in fact we found, the corners of the box such that all edge squared distances from S to T remain the same. But in fact all the Euclidean distances contract. For example, S and P2 are now square root 2 apart, which is less than 1.9. And S and T are now, Euclidean distance is now square root 3 apart, which is less than 2. So for those of you who got lost a little in the computation, all we tried to show in this example was get 4 points, lay down a few Euclidean distance between them, and showed that you could always find an embedding, well, proof by example, you could always find an embedding into a nice Euclidean box, such that edge squared distances remain the same, but pairwise Euclidean distances shrink. So I think I'm out of time here, but that's the basic idea for this proof. We will then show that the nearest neighbor is equal to the edge squared on this box. I'm going to omit that proof. It's actually pretty simple. You basically take your path and you just project it to the axes of your box. It turns out to be pretty easy to prove. That any path here is more expensive than if you just walked along box paths. It's basically the end of the lecture. High level picture, just once again, was metrics for clustering should have certain properties, or so we believe. Two metrics have that property, the edge squared distance and the nearest neighbor distance. They seem very different on the surface. They're actually the same. We gave a little preamble for why we cared. We gave a little proof outline that has to do with embedding, and this really nice theorem called the Kirszbraun theorem. If you don't take anything else away from this, I think the points are we're studying metrics that have nice intrinsic properties, and the Kirszbraun theorem is freaking awesome. So we just have a few open questions to end this. Is the edge k metric equal to the nearest neighbor to the k minus 1 metric? We think this is true. This answers the question of why edge squared and not edge cubed. Turns out when you take k less than 2, it's not true, by the way. Well, can we say things about second nearest neighbor questions? Can we find fast algorithms for computing the edge squared distance? We haven't done that yet. What other metrics are good for clustering? Like maybe we just gave 2 sample ones, maybe there are ones that are a lot better. How far can we push our methods? And is this actually better in practice than other methods that do clustering on these weird point sets properly? There are density-based methods called dbScan for the machine learning people out there. Do we actually do better than those? In fact, in practice, we do find that we cluster these properly, but we don't know that we do better than other density-based methods. Whoops, I'm missing a slide. But the last slide was going to say, this is actually related to something pretty interesting called density-based distances. If you take the limit of the edge squared metric as you lay down a whole bunch of points, you in fact get an intrinsic distance on your underlying probability density. So instead of thinking of clustering discrete points, you can think of clustering, densities in the limit. And you should try finding metrics, or we believe you should try finding metrics that cluster densities properly. The edge squared metric, in fact, does correspond in the limit to an extremely nice distance based on density. And that is all I really have to say for this talk. Thank you so much for paying attention and listening to this talk today. I hope it wasn't too unclear at the end. And that's it. I'll be taking questions at the front for a little bit.
So this, can I just ask a question about the proof?
Yeah.
This is how you map them all to the corners of an n-dimensional
Yep.
hypercube.
Yep.
Just the things that are.
Oh, box, not
Yeah,
a cube,
we take
but a
over.
box, which, depending on where the points are,
Yep.
it determines how big the box is in each dimension.
Yep. Absolutely.
Not all of them, right, just the ones on the map,
No, it has to be-
right?
it has to
You
be
use
all
all
of
the
them.
points
It
or
has
just
to be
the
all of
points on
them.
the storage tabs?
Oh, use all the ones. Yeah, use all the ones.
It has to
You
be
don't have
all of
to.
them because it has to account for all possible shortage paths.
I don't understand where you put the other thing.
Oh, you put the other like, for,
Like in this example, these were all on the storage tab.
let's say I had 1.2 here. Let's say I'm trying to do this really better. Let's say this was square root 2. And this was, let's say, 1.1 or something. It would in fact go to the same embedding. So now this would be 2. This would be 1.1 squared. If I lay down this picture, it would still be the same. Right? If the x squared distance here is 1, here it's 2, and here it's 3. So just lay them down 1, 2, and 3.
Okay.
Yeah, sorry, it's a little bit complicated. I'm sorry I didn't prepare slides for this.
No, that's okay.
But in fact, you do map all the ones. I'm not sure you need to map all the ones, but you do map all the ones. Yes?
So like this, did you sort of more or less have this proof technique from the get-go? And with Kirszbraun, or like you stumbled around for a while and like, Eureka, you found this theorem and,
Oh yeah, no, we stumbled around forever.
okay.
I think a bunch of people stumbled around in 2015 and tried a bunch of calculus methods, which calculus is hard.
So how did you, like, what's the story, how you ran into the theorem? Like,
The Kirszbraun there.
yeah.
At some point, I discovered like I was trying to do this embedding, right? I actually found that hey, what if we just shrink our edge squared metric into as much as we can? Like this diagram sort of represents you shrink all pairwise distances as much as you can without distorting the edge squared metric. And I was like, whoa, we got a box. We actually previously proven it on the box before. So it was like, wow, what if the nearest neighbor distance also contracts? It'd be really nice if this one theorem were true. So I played around with it for 3 points. Tried doing it for more. That's where we came up with the folding algorithms. Then we contacted our friend Don Sheehy from University of Connecticut, who was on the postdoc here, and he was like, actually, this is computational geometry 101. Exactly. The short answer is, in fact, we stumbled around blindly. We had a lemma that worked in the box for a while. Then we got the surprising result that the edge squared distance could be mapped onto the box. And so the missing piece was the Kirszbraun theorem, and it turned out that that was already done for us in that conclusion. The proof for that theorem, by the way, is actually super, super nice and super elementary. I recommend everyone give it like a look. But yeah, any other questions? Yes.
So you have these examples, these nice examples where like a traditional clustering algorithm like k-means will do a bad job
Yep.
because it is manifolds. Do you have some, like, are there, examples off the top of your head where this is not really what you want, really want k-means, like somehow this will do the wrong thing?
So k-means, what k-means does is it usually creates clusters that are like spherical.
Right. Yeah, I guess I'm asking, like, is there a case where this has a problem and really like you want to stick with the...
Yeah, so I'm not, unfortunately I'm not a practitioner, so I can't say for sure. But my guess is something like, if you think your clusters are spherical, like if in fact your metric is set up so that, your metric space is set up so that your clusters will be spherical, then k-means gives you that spherical prior, where our cluster might give you some weird shape like this. So the short answer is if you think your points, if you think spheres are actually like useful, then k-means will probably do a better job. And one way you can treat the x squared metric, if you ratchet up k to be infinity, you're actually taking density level sets. But basically, the more you ratchet up k, the cheaper it is to walk along a short path, but the less spherical your clusters get. So you're trading off between like sphericality of clusters, but also like how closely you follow the density. Did I answer your question? Cool. Any other last questions? Comments, thoughts, extensions? Yes.
So the fact that these two metrics are the same, kind of, and they were discovered independently. I mean, it was the one you guys were doing it, and it was the nearest neighbor one, and the other one had already been worked out by some other people.
Yep.
Doesn't that give you some kind of confidence that this is really a significant, important thing? At least in mathematical thinking, but maybe even practical.
We hope so. We've actually been exploring that line for a little bit.
Let's see what Soda says.
Yeah, we'll see what Soda says.
Oh, okay.
But yeah, we certainly hope so. Actually, there was something I didn't say. So this proof actually breaks down when you hit edge cubed. And the reason edge squared turned out to be nice, and I won't go through the details here, is edge squared is L2 squared. Right? L2 squared is nice. L2 cubed, not as nice. L3 cubed is super nice, but L3 loses the nice properties L2 have. So one reason this proof worked at all, that this nearest neighbor equals the edge squared, was some coincidence relating to the fact that you could embed it into this box nicely. Right, so all I'm trying to say is we came up with these two metrics separately. This box embedding thing was not known at all. It happened that you could embed in the box, and it also magically happened that the nearest neighbor was equal to the edge squared of the box.
Your point is that you're not doing the whole metric though, because if you could embed the whole metric, that would say that it's L1, that would be a very different thing, right?
Yeah, yeah.
I don't think you pointed out that he's only embedding this breadth for a search path.
Yeah.
To get the whole thing, that's not true.
But to answer your initial question, Danny, I think, yes, we certainly hope that, because we didn't know these were equal at first, and the fact that they were equal hopefully points to something bigger, but we're still exploring the space of what that is, and if you have any ideas, we'd totally be open to it. Cool, and did that answer your question? Any other questions? Last things? We're out of time basically, so if people want to head out,
Yeah,
feel free to do so.
maybe take the remaining questions offline.
Yeah, we'll take the
Second
remaining
speaker one more
questions
time.